I welcome you for the video tutorial session on single phase control rectifiers. The controlled rectifiers are of two types. One is off controlled rectifiers and fully controlled rectifiers. In case of off controlled rectifiers, off SCRs are replaced by diodes. The output of off controlled rectifiers are normally of DC current, especially unidirectional current. In case of off-controlled rectifiers, the power flow is happening from AC source to DC load. In case of fully controlled rectifiers, we have two processes. One is rectification process and another one is inversion process. During the rectification process, the electrical energy AC form is converted into DC so that the power flow is happening from AC source to DC load. But in case of inversion process, it is just opposite that of your rectification process, so that the power flow is happening from DC load to AC source. Now we can look into half-wave controlled rectifier circuit. As shown in the figure, this is the corresponding circuit configuration of half-wave controlled rectifiers. In this circuit configuration, the thyristor switch is connected with the resistive load. The entire configuration is powered by AC supply. So this is the corresponding waveform performance of off-controlled rectifiers. Now we can discuss about the basic operation of off-wave controlled rectifiers. So this circuit configuration is powered by single-phase AC supply. So we know very well the AC supply is normally having positive off cycle and then negative off cycle, so that it's being continuous. Whenever the AC supply is given to this thyristor switch, during positive off cycle, this thyristor is of forward biased, so that this thyristor switch is conducting, so that the current is flowing to the resistive load, so that we can measure the output voltage as shown in the figure. But we know very well the thyristor switch is of having the gate terminal, so that the output voltage is being controlled with the parameter is called the firing angle alpha. This alpha can be varied from 0 degree to 90 degree in case of rectification process. Now we can look into this output voltage waveform. Here the T0 is mentioned. What it represents that from the degree 0 to up to this time, we have a denotation that alpha, that is firing angle. So up to that, the thyristor doesn't have any conduction, so that the output voltage is 0. So whenever it is 0, in case of conduction, we can have voltage that is shown in the figure, that is VAK. So it may be continued for the next cycle. Whenever we apply the negative off cycle, this thyristor switch is negative bias, so that we don't have any conduction, so that from the period 5 to 2 pi, the output voltage is 0. It is shown in the waveform. Next, we will discuss the same off-wave controlled rectifier with RL load. As that of the resistive load off-wave controlled rectifier, again we can give the AC supply as shown in figure, as shown in the waveform. So during positive off cycle, this thyristor is conducting, so that we can have output voltage like this. But in case of this waveform, the firing angle is being followed, so that from 0 degree to alpha, we don't have any output voltage V0. But from alpha to pi, there is a conduction. There is output voltage from this off-wave controlled rectifier. But what is this conduction 5 to some 5 plus alpha is? This is only due to because of this inductance. Because inductance is having the property that whenever any change is happening, it will give the opposition force. So that opposition force is denoted by this waveform indication. It is the period of from pi to pi plus alpha. The entire period, it is being denoted as beta. This beta is exclusively called extension angle beta. Next, the same circuit configuration is adopted with freewheeling diode. What is the purpose of this freewheeling diode is to avoid the negative output voltage across the load side, because whenever we use the inductance value or inductive load, there may be of having the possibility that negative voltage. In order to avoid that negative voltage this period from pi to 5 plus alpha, we can avoid with the help of using this freewheeling diode. The remaining waveform is same as that of inductive load and as well resistive load. This is corresponding waveform diagram for having alpha as 180 degree. Whenever we set the firing angle value greater than 90 to 180 degree, we can have operation of inversion mode, what we discussed earlier. Now we can have a discussion on full wave controlled bridge rectifier circuit. This is corresponding circuit diagram which is adopted for the resistive load. This is corresponding waveform configuration, waveform performance of this full wave controlled bridge rectifier circuit. Here we have 2 ohms. This is the entire ohm 1. This is ohm 2. For corresponding ohms, we have 2 thyristors, namely SCR1, SCR2, SCR3, and then SCR4. We can supply this entire circuit with AC supply as shown in the waveform. During positive cycle from the period 0 to 5, we can set the polarity as some positive and then negative. So this positive is applied here, this negative is applied here. So this positive will enable this thyristor, this negative polarity will enable this thyristor, so that during positive cycle SCR1 and SCR4 is conducting, so that the current flow is from the source to SCR1 and directly goes to the load resistance load, and then it comes to SCR4 and closes to the negative polarity of the supply. So this is what mentioned here from alpha to pi. Here based on the application or based on the requirement, we can set the firing angle as alpha as 30, 45, etc. During negative of cycle from pi to 2 pi, so we can have a output voltage like this. How it is so? During negative cycle, the polarity is getting reversed, like negative here, here positive. So this negative will enable this SCR3, this positive will enable SCR2, so that the current is again flowing from positive polarity to negative, so that again the current is flowing as that of in the positive cycle mode, so that only the output voltage is mentioned in a unidirectional way. Again this period is 5 plus alpha. Again here the firing angle is being followed. These are all the current direction or the current waveform, and this is the corresponding output current I0. It is mentioned here. The same circuit configuration is used for oral load. Again the entire circuit operation is same that of your resistive load, but the only difference is that because of this inductive load, the negative voltage is being produced. This is only due to the property of inductance. This is what mentioned here. So this negative peak is because of this inductance. Here the comparison is given. Whenever the inductive load is more greater than your resistive load, we can have a performance what we have shown here. Again, in order to avoid the negative voltage from the period 5 to 5 plus alpha, we can use the freewheeling diode here. So this freewheeling diode will freewheels the negative voltage from the period 5 to 5 plus alpha, and this is the corresponding DC output current I0. So this is the control characteristics of bridge rectifier circuit. So what we discussed so far, from alpha, this is alpha and this is your output voltage. From alpha to 90 degree, this bridge rectifier is acting as a rectification process. From 90 degree to 180 degree, it is acting as a inverting operation. This is what shown as a control characteristics of bridge rectifier. So this is the final outcome of this topic. Whenever any kinds of controlled rectifier circuit is being operated from the firing angle in the range 0 degree to 90 degree, so this is the outcome. That is, the average output voltage is positive. The converter is always operates in a rectifying mode. The power is always positive, so that the power flow is from AC source to DC load. Whenever we operate the firing angle 90 degree to 180 degree, always the output voltage is negative. That is, the inversion mode is happening here, so that the power to the load is negative. That is, the load which supplies the power to the source side. So this is what the entire outcome of this topic. Thank you for your kind patient listening. Thank you.